Let's look at a good example on binomial tree. A non-dividend paying stock has a current price of 300. Okay, current price is 300. Over each of the next 2 3-month periods, its price will either go up by 30 or down by 30. So after 3 months, it can go either to 330 or to 270, and another 2 more months, it can another 3 more months, it can either go to 360 here, or it can go back to 300 again. From here it can go back to 300, or it can fall to 240. Okay, an investment in cash account returns 2% per quarter. The risk-free rate of return is 2% per quarter. A European call option on the stock, so which is maturing on this date, and it's a call option, and based on a strike price of 290. So because the strike price is 290, here the payoff is 70, here the payoff is 10, and here the payoff is 0. The price of the stock is to be modeled using a binomial tree approach with 3-month time steps. Okay, now for this, if I have to find out the value, what all I require, I want to go with the risk neutral pricing mechanism. So I want to find out the Qs in each of the cases, the probability of going up and down, so that I can do the computation accordingly, right? So here in each of the cases, okay, let me try it out. We'll put it into an Excel spreadsheet. Okay, putting it into a spreadsheet, it is like 300. The next period could be 330 or 270. The next period could be 360 or 300 or 240. Right? And payoffs wise, I'll typically take it as the max of this number minus 290 comma 0. So this is giving me a payoff of 70, this is giving me a payoff of 10, this is giving me a payoff of 0. Now I also need to find out the probabilities of first of all, the U and D here. Here, if I am finding out the U and D, so the U is this divided by this. So in this case, the U is 1.1, whereas the D is 270 divided by 300, which is going to be 0.9. The same logic, if I try to apply it here, the U is 360 divided by 330, which is 1.09. Whereas in this case, it is 330 divided by 300 divided by 330, which is 0.9. The same logic, if I am going with another U here, the U here 300 divided by 270 is working out to 1.11, whereas 240 divided by 270 is working out to 0.88. So these are the different U's that we are having and different D's that we are having at each of the point. So based on this, now I should be able to find out the Q's for each one of them, the risk neutral probability of going up and down. Now here it's not, this 2% is typically not a force of interest, it is a discrete. So instead of taking Q as e power r minus d by u minus d, I'll take it as 1 plus r minus d by u minus d. So I'll take it with respect to 1.02. So here the Q is going to come out as 1.02 minus d divided by u minus d. 1.02 minus d divided by u minus d finally working out that the Q here is 0.6, whereas in each of these cases I'll take it as 1.02 minus D divided by U minus D. This is working out to somewhere around 0.61, and here if I am applying it 1.02 minus D divided by U minus D. This is working out to 0.59, right? So these are the different Qs. Now once I know that in each case these are the Qs, now I know these are the Qs in each case, I can typically see that, okay, I'll try to evaluate node by node now. Now here there is a 61% chance that the payoff is going to be 70, and there is a 10% chance that there is a 39% chance that the payoff is going to be 10. So here I'll look at the expected payoff. Here if I am doing the expected payoff, it is 0.61 times 170 plus 1 minus 0.61, the remaining 39% chance that the payoff is going to be 10. So this is 46.6, and this I am trying to bring it to one period before, so I am discounting this by 1.02. So here the value is coming out to 45.68. The same logic I'll try to apply here. There is a 59% chance that I'm going to get a payoff of 10, and there is a 1 minus 59%, which is a 49% chance that my payoff is going to be 0. So expected payoff at the end of 6 months is going to be this. I'm trying to find out the present value by dividing it by 1.02. So the expected payoff at the end of 3 months is going to be this much. Now again, using this with an option with a Q of 0.6, I'll try to find out the expected value. There is a 60% chance that the payoff is going to be this much, and 1 minus 60% chance 60% chance that the payoff is going to be this much. So the expected payoff here is 29.72, and again I can discount it by 3 more months to typically get the value as of the current period. So the value as of the current period is 29.14264. So this is what is the typical binomial tree based option pricing, right? If the up movement and down movements are known, we initially will calculate the U and D for each of them, and we'll try to compute the Q based on whether the interest rate is a continuously compounded rate or a simple discrete rate. If it is continuously compounded, I'll calculate the Q as E per R minus D by U minus D. Otherwise, if it is discrete, I'll take it as 1 plus R minus D by U minus D. So this is what is the first part. Alright. Assume that the real world probability of the stock price moving in each of the next months. So under the P measure, the real world probability is 0.7. The risk neutral was around 0.6 and 0.61 kind of stuff, whereas in the real world, this is coming out to 0.7. Now based on this, I'm trying to find out the value of the state price deflator after 6 months. Now the state price deflator for us is nothing but, now if it has to come here, it has to pass, here if I want to find the state price deflator, it is coming from this and this, right? So I'm trying to take the Qs at each of these points. I know that the Q at that is 0.6, the Q at the next one is 0.61. I'm dividing it by 0.7 and 0.7 because I'm taking two upward movements there. and I'm also considering the interest in each of the cases. So this becomes my state price deflator if I am typically going with each of these nodes. So what I can do, I'll try to find out the state price deflator here. Okay, at this point, two up movements. So zero point 0.6 is the Q of up, then 0.61 is the Q of another up, and now I'm replacing both of them with 0.7s because the probability of up movement is that much, and at the same time, because I have the interest rate created increased by 2% in each of the quarters, I'll take the state price deflator here being 0.71. Now the same logic I can apply here as well. I can go to each of the nodes. So one for the 300 that came up, I can go either via the 330 route and 300 again. So up and down. So from here there is an up, from here there is a down, or there is from down and up. So I can find out two different deflators. Let me try that. So one of the deflators that I am getting here is first of all up and then down. So in case of this, I am taking the up part. This is the up, and the down part is 1 minus this. Right? I have taken the up part from 300 to 330, then the probability of down from 330 to 300 using the Q model. Then I am taking the P model. For P, the up is 0.7, the down is 0.3, and again 1.02 square. So the first path where there is an up and a down, we are getting it as 1.71017. The next path is one is a down and then an up. So I can even compute for a down and an up. So the first part down, which is 1 minus 0.6. The next part up, which is 0.61. These two are the probabilities here. And this I am going to divide by first part down 0.3 in the real world measure, then 0.7, which is an up, and 1.02 square. Okay, so this is giving me somewhere around 1.16. One minus, so from here it has come down, then up. Okay, here the up is 0.59. So this comes out to 1.081. And finally two downs. So I'll find the state price deflator with respect to two downs. So in the first case, the down is 1 minus 0.6, 0.4. And in the second case, the down is 1 minus 0.5, 0.59. So these two things taken together, and I'm looking at 1 minus 0.6. That used to be the probability of down. 1 minus 0.59, the probability of another down, and now we are taking the real world probability measures for them. 0.3 times 0.3 times 1.02 square. So logically this is working out to somewhere around 1.75. That is the down related stuff. Now I got the state price deflators for each of the four different points. Now what I can very well do is in each of the cases, now that I have the deflators for each of the four cases, I can even find out what is the payoff in each of the cases, because we know typically the value of the derivative or the option premium under the real world probability measure comes out as whatever is the state price deflator that is existing at each of the time periods, expected value of the state price deflator multiplied by the payoff at each of the periods. So here I know the payoff is 70. So let me take the state price deflator multiplied by the payoff. State price deflator multiplied by the payoff, and I have to take even the probabilities also. First let me do the state price deflator multiplied by payoff. This is the state price deflator multiplied by the payoff, and this is the state price deflator multiplied by payoff. Now I have to even multiply it with the probability because I need the expected value of all this. So what I'll do is two up movements. So 0.7 into 0.7. So this becomes 0.7 squared times this value, which is coming out to somewhere around 24. Now there is one up and one down. One up and one down. 0.7 times the down is 0.3 times this value. Okay, this is 2.24. Again the same, there is one down and one up multiplied by this value. Then the last one being two downs, so it becomes 0.3 times 0.3 times this payout. Okay, so overall the value of the option is going to be the summation of these four, which is working out exactly the same which we have got in the risk neutral pricing approach. So whether we are going with the risk neutral pricing approach or the real world probability based approach, the solution should not change. The value of the option should not change based on the model which we are using, whether I am using a risk neutral pricing model or the real world probability based pricing model. The price of the option should not change. So these are the two ways in which I can find out the price of the option using the risk neutral as well as the real world probability measures. Now, assume that the real world probability has now dropped from 0.7 to 0.6. Okay, if it has dropped from 0.7 to 0.6, what we could clearly see is the state price deflator. This value is going to go up because in the denominator we see 0.6 and 0.6, which will be lesser value. So this price deflator is going to go up, and these two, because now this becomes 0.6 times 0.4, which is becoming 0.24. Earlier it was 0.21. So the denominator has become higher. So these two values are going to reduce, and even for the lowest node also this value is going to reduce because it becomes 0.4 times 0.4, which will make it 1.16, and this value is going to go down. So this deflator is going to go up, these three deflators are going to go down, but rest all does not change, and overall value also should not change because as we have said, the typical value of the option, it will not change because it will not depend on the real world probability measures at all. Right? So these kind of things we really need to understand and appreciate when we are working with the data trying to do the pricing of the options using the binomial tree model. Alright.